Shukran. All right. Let me just remind you what we did in the first lecture. You start with a semigroup, and it has an infinitesimal generator. And then you try to find an operator A that will have this property. So if I act on the semigroup, I decrease the parameter by 1. And if I can find such an operator, usually that's, if it's defined on polynomials or something, it will reduce the degree, so it will have a non-trivial null space. But in general, it has a one-sided inverse B. So AB is the identity. And what the semigroup is essentially the fractional powers of this B operator. Okay. So if we go back to the fractional calculus, we start with the differentiation. Then we have this semigroup, say Riemann-Liouville, for example, fractional integrals. This property is satisfied. A here is the derivative. So B here will be the integral. So this will be the fractional integral of order alpha. Okay, so again, I start with the operator. It reduces the parameter in the semigroup, and then it has a one-sided inverse, and that left inverse, if I erase it to fractional powers, that's what the T of A is, essentially. Okay, so what is new here is this idea that you introduce an additional operator that has this property, and then this would be fractional integrals. So this is a general concept that we introduced. Okay, to carry this out, we need some examples of this. So I have to first define what a Poisson kernel is. I'll start with a sequence of orthonormal polynomials. So the PNs are orthonormal with respect to a measure mu, normalized to be total mass 1. Then this function is called the Poisson kernel. So it is the sum Pn of x, Pn of y, r to the n, and it's a function of x, y, and r. Beforehand, we don't know where it converges or what happens, etc. But normally what happens is this converges when x and y are in the support of mu, and when r is less than 1 in modulus. So if mod r is less than 1, x and y in the support of mu, this converges. Okay, so to motivate the next statement, I want to do some calculation, just formal calculation. Okay, so I write the function expanded in terms of the orthonormal polynomials. And then I replace these coefficients by the integrals. So I didn't do anything. This is just the definition. And I do something, not very kosher. I interchange the sum and the integral. And I get this. Well, if I look at this, this is very strange because I have f of x on one side and I have an integral involving f on the other side. So that means that this object times the measure must be a Dirac delta function, must be just a Dirac measure. So now it's clear that there is something wrong here with this interchange. You have to be more careful than this. Okay, so here is the motivation. If you look at this object, this is exactly the Poisson kernel, but at 1. So in general, if I look at the Poisson kernel, if I integrate a Poisson kernel with parameter r and a Poisson kernel with parameter s, I get the Poisson kernel parameter rs. This is because of the orthogonality. There is nothing here. This is just Parseval's theorem rewritten. There is no new idea, nothing. What is also true is that if I take the Poisson kernel at r, integrated against f of y d mu y, Okay, so look at this. And let's go back to what was here. What was here exactly the same, except the R is not here, is not there. See, the other one has an R to the N here. So what is true now is that if I integrate the Poisson kernel against the measure, against the function against the measure, and I take the limit as R tends to 1 minus from the outside, then I get F. This is a mathematically correct statement, and it can be proved. Okay, so also, essentially, this says that instead of expanding a function like this, which usually this expansion is in L2, but you want pointwise expansion. So if you try to get pointwise expansion, you stick in an R to the N, and then you take the limit as R tends to 1 minus. This is some sort of a summability method to get around this. And you can prove this theorem here, that if I integrate the Poisson kernel parameter R against F d mu, and I let R tend to 1 minus, I get F. You prove this using Korofkin's theorem. This is a very old theorem. I don't know how the original proof was, but this Korofkin theorem proof we figured out. I'm not sure it's new, but this is an important fact that we use. Okay, so now what I want to do is I want to use this fact and this property that if I integrate Poisson kernel parameter R, again, when I 1s, I get Rs. I want to use this to get a semigroup out of this. So it's clear if I replace R by Q to the A, S by Q to the B, this would be Q to the A plus B. So you could see now that if I take R to be a power of a certain variable, then I do have a semigroup in that variable. Okay. So what in the paper I'm talking about, what we did was we took the Poisson kernel, replaced R by Q to a power, and integrated F against the measure, but we put in some extra factor. We divided by G of Y multiplied by F of X. But G is supposed to be a function which is bounded and positive. Bounded below by a positive number and where this is supported. And the point of it is that if I do it this way, I get something more general, and it's also much more convenient. Of course, you can always take G equal 1, but I don't want to do that. So this is our idea, to introduce this thing and divide by that. Okay, so this is always semigroup as long as G is non-negative and is bounded below.
Excuse me, do you take any function G?
Well, so far, yeah. But of course you need integrability. You need, you can't just take a real nasty function.
Okay.
I'm not, when it comes to doing specific examples, you have to specify everything carefully. Yeah. So I'm not careful here. And I know that.
Okay.
Okay. But when I get to examples, I'll do this exactly. It will turn out that choosing G is very tricky. Choosing G that works for certain operators that you want it to work for is magical. This is what made us really happy, is that we introduced the G and we were able to manipulate it and get good things out of this. Okay, so sorry? In 2007, Suslov looked at an example of this with G equal 1. And these are continuous Q-Hermite polynomials. So he did one example where there's no G, and this is a specific set of orthogonal polynomials, and he didn't realize that this is a general construction. So Also, he somehow assumed the functions are analytic, these Fs, which is really very smooth. I mean, when you try to do these things, you usually just continuous functions or, you know, piecewise continuous or something like that, not something analytic. So, and he showed that there is some semigroup involved here. Okay, and the Poisson kernel for the Q-Hermite, continuous Q-Hermite polynomials is non-negative. So this theorem is valid. So that's what makes the semigroup go to the identity operator when this parameter goes to 0. It's this theorem. Okay, so that was 2007. And the approach I'll show you is from a series of papers I'm writing with Ruming Zhang and Kiru Zhu. Ruming Zhang was my PhD student. He graduated around 1990 or 91. Zhu is an undergraduate student. He's in 4th year. And he came to Orlando last year. He came the last academic year. And on exchange, we have some exchange with China. And he was a 3rd year student, but he took only graduate level courses, including my Q series course. And of course, was the best student in the class. And so he's involved in this. And so we're writing about 4 papers on this. Okay, so the problem is, after you do this construction, you want some sort of fractional integral operators to come out of this. Okay, so I want to find this operator that acts this way, with the TA is this one. Okay, then what happens is, this is where the G comes in. So it's this function. Okay. This is a theta function, and when the operator that you want is the Askew-Wilson operator, this is the one that works. This is the G that makes everything works. So now I'm choosing G, and this is positive because X is in -1, 1. Q is between 0 and 1. This is positive. It's bounded below by a positive number. And it's infinitely differentiable. I mean, it's very smooth. There is no problem with it. So anytime you have you can choose G to match an operator that you have, then you got something. Okay, so this is a theta function, as I said, and to make this a semigroup, we needed some to multiply by a certain factor. And the Poisson kernel for the Q-Hermite polynomials is given in closed form. It's a bunch of products, infinite products. Y here is cosine phi. And the case that Suslov had, G was 1, and his operator A was not Askew-Wilson. He didn't realize this. He kept trying to get Askew-Wilson out of it, and he couldn't. If you read his paper, he says, oh, there's some limit that can be done, and it will be done in another paper or something, and that other paper never written and never appeared, nothing. And the reason is that it's just not true. It's the corresponding operator is not the Askew-Wilson. It's a different operator. So now we understand exactly what Suslov was doing. And we understand why his technique did not work for the Askew-Wilson, because it's just not there. If you want to do the Askew-Wilson, you have to use this G, and you have to use this special choice of G in order for these things to work. Okay, so then we figured out what kind of operator will work for Suslov's result. So it's a combination of this F check with Q to the plus or minus a half times the shifts with the dilations with in the Z variable. Okay, so the way this evolved originally, I had a paper with Mizan Rahman where we tried to identify a one-sided inverse to the Esky-Wilson operator. And this one-sided inverse turned out to be an integral operator. And it turned out to be exactly the case A equal 1 of this thing. It turned out this A was 1 here. So the special case already appeared in my paper with Mizan. And now we are looking at all the fractional powers. There are other forms for DQ inverse. In particular, there is a paper with Malcolm Brown from 1995 and some papers with Zhang where we looked at this inverse, and we don't have yet fractional versions of that. We just know this from the old papers. We want to find some parameter here. So that we haven't done yet, but we're looking at it. So in the paper with Zhang and Zhu, we identified this family, this fractional powers of the Esky-Wilson. So this semi-group we identified. The operators, we proved that for every A, this operator is compact. It has eigenvalues. These are the eigenvalues explicitly. We know its eigenfunctions. We identified the eigenfunctions explicitly. So these are the skew-Hermite polynomials. And A is compact because it's limit of finite rank, and it's not self-adjoint. That's a big hurdle. Because if it's self-adjoint, certainly it's bounded. If it's self-adjoint, you have spectral theory, you have all kinds of other techniques, but it's not self-adjoint. But it's similar to a self-adjoint one. Not unitarily similar, just similar. And that makes the spectral analysis much more complicated. We're again still looking at this, but we don't, we haven't made much progress on this. Okay, so in the same paper, we proved that these are contractions, but there is certain condition because, the smallest eigenvalue here is when m is 0. So if m is 0, this is out, and you have this. And we know, that the norm is at least, the norm of the operator is at least as large as the largest eigenvalue. So this largest eigenvalue has to be less than 1. So if you assume this, you assume that this thing is less than 1, then it's true. These are contractions. You can prove this. Now, the smallest eigenvalue here, it's not the same as the norm. They're asymptotically the same, but they're not the same. So we had estimates for the norm, and we showed that indeed, when this object here is less than 1, then
so lambda m tends to 0?
Sorry?
Lambda m.
Well, the m enumerates the eigenvalues. So the largest eigenvalue is when m is 0.
And so the lambda m does not goes to infinity as for eigenvalues.
No. This is a compact operator.
This is a compact operator, yes. Okay.
No, this is a compact operator. No, everything is bounded,
Okay.
No, when m tends to infinity, it goes to 0, you see.
Okay.
But when you are saying that it is not self-adjoint, so is it symmetric? Is it a problem?
No,
it's not symmetric.
No. It doesn't even commute with it's not normal. It doesn't commute with its adjoint.
So,
no, it's
no. It's not a problem of a self-adjoint extension or something. It's not a problem of the domain.
No, it's something much worse. Yeah. No, because it's not normal. You see, there is no spectral theory because it's not a normal operator.
These are the eigenvalues I mean, are all the eigenvalues real? Is the
Oh
spectrum
yes, yes.
real?
It's a compact operator. It's yeah.
Yeah, but okay.
It is compact, and everything is real. But spectral measures is another story because it's not even clear how you define the spectral measure. It's okay. So anyway, it's not normal. It's not self-adjoint, and we're trying to understand it. I mean, I don't. This shouldn't stop people from thinking about it. Anyway, so we're still looking at this. We're not clear exactly what happens. But the first paper has these results, and it's already submitted, and it's on the archive. Okay, so we proved similar things for the Suslov case. And in this case, in his case, the operator is remission. So, I mean, it's self-adjoint. I mean, there's everything is very simple. Now, the next thing is, what's the analog of the powers for the Eskew-Wilson? Okay, so Dennis Stanton and I introduced this basis. So you see, this is a product of n terms. And this is what corresponds to x to the n in this Eskew-Wilson business. I'll tell you what that means. Okay, so what I want is, what is the analog of x to the n? If I take x to the n over n factorial, differentiate it, I get x to the n minus 1 over n minus 1 factorial. So I want something like this. So what happens here is that this thing here, if I put it in, and if I take an Eskew-Wilson operator acting on it, it behaves exactly like this. Except instead of the factorials, I have this Q-shifted factorials. So this is indeed the analog of the powers. Askin-Wilson introduced a different basis, but it's not, the other basis has a parameter, and when you act with the Eskew-Wilson polynomial, you change the parameter. This one doesn't have any parameters, so when you act, nothing changes. So that's the advantage of this. Also, Dennis Stanton and I, we introduced another basis, which I don't want to write it, but again, the same kind of thing happens. So for this kind of basis, I can define this for n here. This is a product of n terms. I can multiply and divide by an infinite product to make it quotient of two infinite products. And if I do this, then this thing is defined for any n. N doesn't have to be an integer. So if n here is just a positive number, this makes sense because that's this positive number, that's this positive number, everything else is okay. So the definition of x to the alpha, if n is alpha, is exactly this with alpha here and alpha here. Okay? And it has some reproducing properties. We also, in the paper with Stanton, we did the Q-Taylor series expansions in these bases. Okay, so now this family that we introduced, family of operators, if I act on this, so this is like x to the n, I get this. So you see, this was beta, you act with alpha, this becomes alpha plus beta. So this is exactly like an integral. If I integrate x to the beta, I get x to the alpha plus beta. If this is x to the beta integrated alpha times, I get x to the alpha plus beta times some constants. So that's what this is. Okay, so these operators also act really like Eskew integral, like inverse integrals of the Eskew-Wilson operator. And this formula is the analog of if I calculate the Riemann-Liouville fractional integral on x to the beta plus 1 over gamma beta plus 1, I get x to the alpha plus beta over gamma alpha plus beta plus 1. This is the exact analog of this. So it matches. Also, there is this Gauss-Weierstrass transform. We also found a version of it, Q version, and we did the inversion of the operator. And so there are all kinds of technical results that I don't want to get into. But what's important is something conceptually important is what's called transmutation relations. Okay, so let me remind you what these are. Yes. No, I think I went too far. No, I missed it. Just a minute. Bear with me here. Yes. You see, if I take like Jacobi polynomials, if I take a Jacobi polynomial with parameter alpha and beta and parameter gamma delta, I can expand this in this because I have polynomials of all degrees, so it's a basis, so I can always do this. Okay, so here x is fixed and the index changes and you're summing over the index. What the transmutation relation is, it's a continuous analog of this, meaning I have some operator acting on the polynomials. The degree here is n, and what I produce is the polynomial of degree n, same n is fixed, but different parameters.
Sorry, do you also sum over gamma and delta here, or is it?
No. Gamma and delta are fixed parameters.
So they depend on alpha and beta?
No, that's the point. You see, the Jacobi polynomial is a polynomial that depends on the degree and on two parameters, alpha and beta. Okay, but the point is the leading term says x to the n. So once I have this, I can expand this in terms of the same polynomials with different parameters. The parameters are
okay.
Just a basis. It's
okay.
Not, yeah, it's a basis for the space of polynomials. There is no. Okay, so here n is the same, but you're integrating over the variable, and the kernel has the other variable x, and the answer is the polynomial at x, but different parameters. So these are called connection relation or transmutation relations. And these are not known for the Esky-Wilson polynomials, for example. And using our approach, we can get some. So using our approach, we can get, yes, here. Okay, so this is what a transmutation relation is. I have two polynomials, Pn's and Qn's. So the degrees are the same. So this may have some parameters, and this would be the same polynomial, but different parameters. Okay? And I want to write this as the integral of this with some kernel times the measure. But what's important is that n appears only here and here. It doesn't appear in the kernel. Okay? So for the operators that we introduced, we can do this with the Askew-Wilson polynomials have 4 parameters. In the first paper, we have some restriction to choose the G. And if I have here C and D, I can act with this operator and I produce degree n different parameters. This stuff can be absorbed in renormalizing the polynomials. So it's not, I mean, the n's that appear here can be absorbed in renormalizing the polynomials. So the result is that the formula is indeed a transmutation relation. Okay, so this is in the first paper. And also you can use this to solve certain dual integral equations. We modified the technique that was used by Nobel and Snedden in the 1960s. And we used some similar ideas using, see, they used fractional integrals. So we used these integrals that we introduced, and we can do the same thing. We can do, you know, similar things. There are also these dual series equations. Again, there is some similarity, you know, again, we can apply this to them. And now this family has an adjoint family. Just like for fractional integrals, you had the Riemann-Liouville and the Weil. They are adjoints. So this T family that I introduced, there's an adjoint family, and again, the adjoint family, we studied its spectrum, we studied the whole thing for the adjoints. And there is some other work going on. So in some work with Zhu, we played with the G, we chose a different G, and we got, for example, this kind of connection relation. I mean, this kind of transmutation relation for Askew-Wilson polynomials. So you have parameters T1, the Askew-Wilson have 4 parameters now, 4 general parameters. And this is an integral operator acting on them. And it produces Pn. The first 2 parameters get multiplied by R, and the second 2 parameters get divided by R. Again, this is still special. We really would like this to be S1, S2, S3, S4. But this is sort of the poor man's version of it. We don't know what the general one looks like, and this is so far what we could do. Again, these things that depend on n can be absorbed in a renormalization of the polynomials. So this indeed is a transmutation relation that comes out of our approach. Okay, so other things that were worked out, there's more general polynomials, like there are these Al-Salam-Chihara polynomials and continuous dual Hahn, continuous Q dual Hahn polynomials, and so on. Those, their Poisson kernels are not known to be positive. We don't know if they're positive or not. So this approach using Korofkin's theorem does not work. So we had to develop a different approach using L2. And that approach accommodates the other ones. We couldn't determine the positivity, and we asked George Gasper, who is a real expert in positivity results, and he had no idea how to prove the positivity of these. He said he thought about this on and off, and he cannot do anything. So the question of positivity of the Poisson kernels is a very hard one and is not known. So we also did the continuous Q ultraspherical polynomials, and eventually what we really want is a transmutation formula for the general Askew-Wilson. So this we don't know. This we're way far away from that. But we hope, you know, we'll get to it one day. Okay, now another thing is there is this Leibniz rule. If I differentiate the product of 2 functions n times, I get this expansion. So this is something that Q version of it was done. Osler generalized this to fractional powers instead of n. And he had a series of papers in the 1970s and 80s. And Nabi and Mansour looked at Q analogs of this for, not for the Esky-Wilson operator, for this other operator. And what we want to do is hopefully get something like this for the Esky-Wilson, which we don't know. One important question is, what about the Dunkel operator? Bouzaffour is an expert in this, so I hope he can look at it and to see if there is any way to get fractional powers of one-sided inverse of the Dunkel operator. I mean, that would be really nice. There are also some elliptic cases I'm in touch with Eric Cranes about, and this is just in the future. We haven't looked at things seriously yet. So what we hope to do is to develop this to a degree where it becomes where we really understand what's going on. Now, I thought there was yes. There is another approach to fractional powers, but that requires the spectral theorem, and that's why we were trying very hard to get some handle on the spectral theorem, but we did not succeed. Okay, so if I have if I have if I have a what we would like to do, we had the semigroup, this TA, and if I take T1, so that would be the one-sided inverse to DQ. And if this operator were normal or self-adjoint or something like that, we'd have a spectral theorem like this. And then I can replace this by any continuous function in it. So in particular, I can raise T1 to the alpha, to the A by this integral. And this would have been very nice. But of course, T1 is not self-adjoint, as I told you. And it's compact, and we don't know. We're trying to do something about this approach. We're trying to see if there's another fractional type of family that comes from the spectral theorem. And if there is it the same family, or is it a different family, or what is involved? We don't know. Again, this is still in sort of various. We're just doing some scratches on this. We don't have any concrete results. So this is something that we don't understand, and we don't know if it will work. But I really would like to see the Dunkel operator looked at. Okay, that's it. Thank you.